In this video, I'm going to walk you through a quick guide on how to construct circuits to kind of keep your components safe. Now, you will ultimately be safe. We're working with very low voltage here. You wouldn't even be able to feel it, if you touched it. But we want to make sure that we're keeping our components safe. Like, you will fry apart, it's a rite of passage, but we want to make sure that we're not repeatedly doing it to the point at which it becomes frustrating. So I'm going to kind of give you some basic tips on how to set up an environment and construct circuits here. So the first thing that's important is the solderless breadboard. This is how we're going to connect up all of our circuits. And it's really nice. There's like these nice little sockets here where you can plug in components and connect them together. So it's important to kind of understand the internal connections going on here. And so this is called a breadboard because originally when you were constructing circuits, you would take a wood cutting board and drive nails into it and then wrap the legs of various components, like an LED, onto the nails to make the connections. And so this is kind of what they've been adapted into, these nice little sockets where we can plug things in. And they're called solderless because you don't have to go through the effort of actually soldering before checking to see if your circuit works. It's just a really nice way of prototyping to see if everything works. And then maybe if you can go on to like a soldered solution once you're happy with the way your circuit's performing. But on the left here, we see a little like half-size breadboard. They also come in full size. And on the right, we see kind of the internal connections going on behind the scenes inside of the breadboard. So on the outside here, we'll call these areas the power rails right here. And so we see the plus and the minus, and these are connected to whatever is supplying power to your circuit, typically some battery or some power supply, where the positive part of the battery gets connected to this left side positive rail, and the negative side of the battery gets connected here on the right hand side. And so you can connect both of these outer rails together or just use one of them, or if you need two different voltage levels, you can do that. But this is where we'll provide our power. And they are connected together internally vertically, meaning that if I plug in one thing right here, and then I plug in something else here, it's like it's connected together because inside there is, some metal rail that goes the whole length of this here. So that's where we'll get our power from to construct our circuit. And then where you typically construct your circuit here is in this middle area here. And so it's kind of broken into two halves with this little gutter in between. And this is made, the spacing is nice because it's made for switches and different little integrated circuit chips to fit just across there. And we'll see that kind of later on as we start to use some of those parts. But yeah, it's divided in two halves. And if we look over on this side here, we'll see that these things are connected together horizontally in rows. But it's important to note that this row doesn't jump across the gutter and connect here. So if I connect, if I plug something into A1 and D1, it's connected together. But if I plug something into A1 and F1, it's not connected. And so we need to keep that in mind as we're constructing circuits, and I'll show you some examples here. But this is basically how a solderless breadboard works. So now we'll talk about how to power it. So some kits will come with like this sort of power supply here that can be helpful to play around with. It looks like this, and it snaps right onto the top here, but it does take up a lot of the usable space of the board, kind of takes up this whole top area. So we're going to be using a battery, but I wanted to show these. It comes with, you basically power it via some sort of like wall wart adapter that takes AC voltage and turns it into DC, and you plug it right in there and you can switch it on with this little button. But what we're going to be doing is we're going to be using a 9-volt battery again. So this is our 9-volt here, and then we have this right here, which clips right onto there. And the one thing that's important is we want to make sure these two ends sometimes like to touch each other. We want to make sure that they're not touching because as we just learned, our current is proportional to our resistance. And if these two wires are touching, there's virtually no resistance, right? Wires are meant to be very good conductors and have very low resistance. So that means there's going to be a lot of current, and it's going to very rapidly discharge this battery. And kind of get hot. So we'll want to make sure that these are apart. And so what I'm going to do is I'm going to go ahead and plug them into my breadboard here. So I'll plug the red wire, which is our positive. It'll go to the positive terminal on our battery, into the red rail, and our black one, which is negative, I'll plug that into the negative or black rail there. and then I will snap this right on here. And now in this entire vertical rail on the left, we have 9 volts, and over here we have 0 volts on this black rail. And so that's kind of the basics of getting started with this. And then we can start to construct a circuit, and I'll show you that process here in a second. So there are resistors. This is a component that we're going to be using. So we talked about resistance. A resistor is just something that provides a constant resistance. It is a 2-terminal component, meaning that it has, you know, one leg and then another leg right here. And between those 2 legs, inside of the body of this, it provides a constant resistance. And so it's represented in a circuit diagram with these little squiggles here. And what we're going to do is we're going to use this to divide voltage or reduce current. And I'm going to show you how we're going to use that with an LED. So let's talk about, well, first, let's take a look at this color guide here. And so on resistors, there are bands that help indicate the value of the resistor. So here are some typical values you might find, and you could kind of work backwards to figure out, you know, what color bands would be on there. Like if you look on these two, they have different color packages, but you can start to see that there are different colored bands on there. I know it won't focus too well. But another way of just telling its value, right, is you could use a multimeter, which it's called a multimeter because it can read voltage, resistance, and current. If I just attach a multimeter in resistance mode to both of the legs here, I can see, okay, this is a 330 ohm resistor, and this one here is, let's see, about 1 kilo ohm, 1000 ohms, give or take. And so that's a helpful way of doing it as well, so you don't have to go cross-eyed looking at the bands. So now let's talk about LEDs. So an LED stands for light emitting diode, and it's a special type of semiconductor that emits light when current flows through it. And what we mean by semiconductor is its properties lie between that of a conductor and that of a insulator, right? So it's not always going to conduct electricity. It does it under very specific conditions. And for an LED, that specific condition is when it has enough voltage across it. And so LEDs have a specific polarity, meaning that we must connect the positive voltage to the anode and the negative voltage to the cathode. And over here on the right-hand side, you can kind of see this is what it would look like in the circuit diagram, but this is what the physical part looks like. So the longer leg on an LED is used to kind of help indicate which side is positive, and the shorter leg is negative. There's also, if you're looking down from the top of an LED, there's typically a flat side, which indicates the negative. And so LEDs, like I said, are a semiconductor that want a very specific voltage to turn on, and it typically depends on the color. And they are going to maintain that voltage across it, but it typically, depending upon the color, it's somewhere between 2 to 4-ish volts. And so if we give it more volts, like right now we have a 9-volt battery hooked up in our breadboard. If I just gave it 9 volts, it would just instantly kill the LED and it would no longer work. So what we need to do is introduce a resistor into that circuit to reduce the voltage and keep our LED alive and control the amount of current that's going to flow through it. And so I'm going to show you kind of the process of calculating that. And once we've done it once, we're good to go. You don't have to continue to calculate it. But I do want to kind of explain this process a little bit here. And so we're going to flip back to here, and let me grab my marker. And so this is how we can draw a circuit. So this right here, this part represents our battery. And so this is where our 9 volts comes out, and then down here is where our 0 volts is. And I'll indicate that with our little ground symbol here. So this is 0 volts, and up top here, this is represented by 9 volts. And so what we're going to do is we're going to introduce a resistor, shown by these little poorly drawn squiggles here. And then we're going to have an LED right here, which we draw as like this little triangle with this flat part like this, and then come back around like this and connect our circuit so that there's this complete path for current to flow. And sometimes there's little arrows shown to indicate that there's light being emitted out of it. And so we're going to use a green LED, and they want somewhere around like 3.5 or 4 volts. So we're just going to say 4 volts here for ease of calculation. So to get from 9 volts to 0 volts, we have to drop exactly 9 volts to get back to this point. All of the voltages around in this loop have to kind of add up to 0. So what's going to happen is if this one's 4 volts here, this is going to be 0, again, because it's connected down to this point. This point here is 4 volts. This is going to force 4 volts across its wires here, or across the legs, the leads of the component. So across the LED, there's going to be 4 volts, which would leave 5 volts to go across this resistor here, right? And so we could kind of work backwards and say we want, some amount of milliamps to be run through this to make it bright. Somewhere between 5 and 20 milliamps is kind of the target here. So if I just said, let's make this a 1 kilo ohm resistor, just to make our calculation really easy here, we could calculate the current that's going to flow through the system using Ohm's law. So remember, our current is equal to the voltage over the resistance here. And so because this is a circuit, a complete circuit like this, the current is going to flow through all of this, and it's going to be the same. The same current flows through all of these components here. And so if I just look here, I have 5 volts going across this resistor, so that's going to be my voltage is 5 volts, and the resistance here is 1 kilo ohm. So if I divide 5 volts by 1 kilo ohm here, I'm going to get 5 milliamps of current flowing through there. So if I wanted to adapt this then maybe to be a 330 ohm resistor, which is another common one, we could go through and calculate that again and say I equals, again, there would still be 5 volts across here because the green LED is going to force about 4 volts across there. So we would have 5 volts divided by 330 ohms. And if we solve for that, we would get something like 15.15, kind of going on forever here, milliamps. So we're going to try and hook up both of these, and we'll see, how it behaves, right? So think about what you would expect. If you would expect it to be brighter or dimmer based on which resistance value we're using in our circuit. All right, so here is our breadboard with our power supply. And so if we look over here, this was our 330 ohm resistor. So what I need to do is create a completed circuit. I'm going to go from the positive here and just go somewhere into this middle part where we're typically going to construct our circuits. And one thing that's a good idea to do is not provide power to your circuit quite yet. And so you can just kind of pop this guy off here just to make sure that we have everything wired up properly before we continue on. Let's see if that, a little bit better. All right, and then I'm going to take my LED here. And so we want to remember, take the long leg of the LED, and that's going to go to the resistor, and the shorter leg is going to go to the negative rail, or the 0 volts here. And so in order to plug this into the resistor, I don't need to plug it into the same socket. There's not enough room for me to do that. I just need to plug it into the same row in the middle part because this is connected together internally. So I'll take the longer leg and plug it in there, and I can take the shorter leg and plug it in here. And so now if I do this, and I plug it on there consistently, we see that we have, a nice bright LED here with our 330 ohm resistor. So let's do it again here with our 1 kilo ohm resistor. And I think what we should expect here is that it should be slightly dimmer. So I'm going to kind of hook it up in the same fashion like this. It's kind of hard to see from the top down view, but I'll bend that out of the way. So we go from the 9 volt red rail through the resistor, then it's plugged into the same row, and then the current flows through the LED to the black negative rail where it goes back to the battery and then gets ejected back out as 9 volts, completing that path there. And so when I plug it in, we see, yeah, this one is slightly dimmer because we used a higher resistance. And as the resistance goes up, the current goes down, which is going to make the LED dimmer. So just kind of in closing here, I want to kind of walk through just a very brief guide to make sure that things, last a very long time, right? So, as a professor of mine once said, once you let the magic smoke out, you can't get it back in. Sometimes when you're working with little integrated circuit chips, they're little black parts, there will be some smoke that'll come out, right? So LEDs will kind of just stop working. They're not going to like smoke out really crazy unless you hooked it up to very high voltage. But yeah, we want to kind of avoid certain things, right? So the first thing is don't short things. And what I mean by short things is basically have no resistance. That's what I was talking about with the battery and those leads touching directly together. If they touch directly together, there's virtually no resistance, which is going to make a very high current. So we want to avoid that. We want to avoid loose wires that might, come in contact with each other and short it. And we also want to always kind of power off our circuit before we modify things, just to make sure that we don't accidentally plug something in somewhere before that. And then we can always double check and triple check our circuit. And then one thing that we always want to avoid is something called spaghetti, right? So we have a lot of different jumper wires, right? And I could have introduced some of these wires inside of here to help route power in certain places. But the more of these jumper wires you use, while they can be helpful, the more that you use, the more points of failure there are. Because sometimes these aren't manufactured too well and there can be some issues with it. And there's just more chances for you to plug in things wrong the more wires you're using. And so if you're using spaghetti and they're all crisscrossed all over the place, kind of constructing a more complex circuit, you might miswire something. So, only use as many wires as you need. Try to minimize the number that you need, and that'll kind of make sure that your components live a long and happy life.